Welcome back to Math for Technology. We are finishing up Chapter 3, and our last section here is the similar geometric shapes. So some of these might be two-dimensional shapes, some of them might be three. So the idea behind similar is that they're the same shape. And so you can see in this case I have two quadrilaterals. They are exactly the same shape. We have some marks telling us that we have same angles. So this angle here up on the top is the same as this angle up on their top, so that means they're the exact same measure. What you should see is that they're not the same size though, even though the angles are all the same. This smaller shape over here, this upper side is 2 meters, over here it's 4 meters, so it's twice as big on the right hand side. That ratio should hold true through all sides. Since this is 3, this is twice that. 1, twice that, 5, twice that. Whatever the ratio is on how much bigger or how much smaller it is, it has to be the same all the way around the shape. So polygons with the same shapes are called similar polygons. Their corresponding angles are equal. And so that's what we have to remember is the angles are exactly the same, but the actual sizes of the sides are bigger. Here we have two pentagons. They're not regular, in other words, they're not the same all the way around. AB is 12, so that's this side. DE is 3. Now these marks, what they're telling us is that in the second shape, right, so they can't use A and B, so instead of using different letters, they use the mark to represent the second shape. So this one is 8, and they want us to find DE. So what we do to solve this is we use ratios or proportions. So we're going to make a ratio of one shape, a ratio of another shape. Together we're going to make a proportion. I'm going to go ahead and just do this as a ratio. So I'm going to do 12 over 3. So I put one shape into a ratio. When I come over here to make the other side of the proportion, since I put the bigger side on top in this shape, I have to make sure I put the bigger side on top in this shape, which is the 8. Now think back to how you solve ratio or proportions, which you did when you converted radians and degrees and vice versa. So in order to solve those, we multiply diagonally, or what's called cross multiplication. We have 12 times x equals 3 times 8. 12x equals 24, so x equals 2. So this distance right here is 2, whatever the units are. Notice it's not a whole number, it's actually 1.5 times. So this bigger shape is 1.5 times bigger than the smaller shape. It's not always a whole number like it was in the sample in the beginning. Here what we have is we actually have a triangle laying on top of a triangle. So I'm actually going to pull those apart. So this is A, D, and E. This one's a little bit longer. This is A, B, C. So they laid one triangle on top of another triangle. Go ahead and label what we know. AD is 20. AB is 24. BC is 18. What is AE? So they want us to find AE. They also want us to find DE. So they're asking us to find more than one thing in this case. The other piece that should have been on this picture that's not is that these are right angles. It's crucial in this problem. So one thing we're going to go ahead and do is we'll go ahead and we'll first use the idea of the proportion to help us solve for our DE. Now, in example 1, I made the ratios based on the shape. So I kept these together and these together. That's one way to do it. I can do it based on where they're at in the... So I'm going to do this bottom with this bottom. So I'm going to do 20 over 24 equals... Now I'm going to move. I also know this side, and then I'm looking for that side. Since I put the 20 on the top, which is from the first shape, I have to make sure the first shape, or the Y, is on the top. And then I'll have the 18, because it's from the second shape. So these are both from the first shape, these are both from the second shape. These are from the same position in each shape, same position in each shape. I'm going to go ahead and do my cross multiplication. So I have 20 times 18 equals 24 times y. 20 times 18 is 360. Now I need to take 360, divide it by 24. 360 divided by 24 is 15. So this DE distance is 15 units. The other thing they're asking us to find is AE. Since these are right triangles, AE is actually the hypotenuse. Since I have a right triangle and I'm looking for the hypotenuse, I'm going to go ahead and be using the Pythagorean theorem. The Pythagorean theorem is a squared plus b squared equals c squared. I don't know the hypotenuse, that's my x. So I have 15 and 20. Doesn't matter which one you put where, just make sure they go in for A and B. 15 squared is 225. 20 squared is 400. 400 plus 225 is 625. Square root of 625, I think is 25, but I'm going to make sure. Yep. So AE is 25. So the two things they're looking for, AE is 25 and DE is 15. So as we keep building in this math and as this semester goes on, just because we've moved past a topic doesn't mean we're going to forget it. We're going to keep using it. We're moving now into instead of just having polygons, we have actually three-dimensional shapes. And in this case I have some prisms. They're not cubes because notice the 6, the 5, and the 12, they're all different. They'd be the same if they were a cube. This one you may be able to do without actually using a proportion, because as you look here, this 12 and this 24 are in the same position. Well, 24 is twice 12. So I can quickly say that, okay, 5 times 2, so this side is 10. 6 times 2, this side is 12. If you weren't able to do that math in your head, you would go ahead and set up a proportion. It doesn't matter that it's in a 3-dimension. You're just going to do 2 at a time. So I'm going to do 12 over 24. That's the two sides that I know that are standing up. 5 is from the same shape as 12. That same position on the 24 is P. So then I would cross multiply, and I would end up right at the same spot at 10. I would do the same thing if I wanted to set up a proportion for finding Q. I would still use the 12 and the 24, and then I would use 6 over Q, and I would cross multiply. You can also use this idea when we're dealing with areas or volumes if we're working with three-dimensional shapes. So if we want to compare the areas of two shapes that we know are similar, well, the formula for area, depending on what shape we're working with, we have this idea here, pi r squared, pi r squared. So that means I'm working with some circles. And so what I'm going to do here is they're telling us that one of the ways we can do it is if we're working with areas of two shapes, we can compare their radiuses squared. So here we're working with the lateral surface area. We know the smaller one is 330, and we're looking for the larger one. So when we do our areas, I'm going to go ahead and do 330 over what I don't know. So this is the area of the large one. So these are my areas. Now I'm going to do my radiuses. This is the small one, this is the large one. So the radius of the small one is 5.6, and I'm going to square that. And then the large one is 9.5. Now you might be asking yourself, how do you not know not to use the 8.4? Well, I don't know anything about the bottom of that. So I don't know that same position on this frustum. Unless I went ahead and found it, then I could go ahead and use 8.4 in what I found. But using the information I know these two right now, so I might as well just use them. They're in the same position. So we're going to go ahead and do the math. So not only am I going to cross multiply, I'm going to go ahead and do the squaring at the same time. So I have 330 times 9.5 squared equals the area of my large times 5.6 squared. 330 times 9.5 squared, 2978.25. No, that's not right. I got the decimal in the wrong spot. Let's rewrite that. 2978.2.5. Area of the large times 5.6 squared is 31.36. Now I have to go ahead and get rid of this, so I'm going to divide by 31.36. 2978.2.5 divided by 31.36. So the area, the lateral surface area of the larger shape is approximately 900. Since they went to a whole number there, I'm going to go to a whole number. That's going to round it to approximately 950 inches squared. I actually came up with 949.697, so I rounded it to 950. So I can do that with areas, and similarly I can do it with volumes. But since volumes are things that are cubed because you're filling in 3 dimensions, notice that the r's are cubed in this case. And the smaller numbers are just telling us if we're doing shape 1 or shape 2. The volume of the smaller frustrum is 757.7. We're using the same frustrums as up here. So the only difference is we're going to be cubing them instead of squaring them. So I'm going to do small to large again. 757.7 over the volume of the large one. And then the smaller one was 5.6, and the larger one had a radius of 9.5. Now we can't forget, because we're dealing with volume, we're going to cube these numbers. Go ahead and cross multiply. So 757.7 times 9.5 cubed is volume, not area. Volume of the large one times 5.6 cubed. So I'm just plugging into my calculator. This side is 649633 approximately. 5.6 cubed. 175.616. Go ahead and divide to get that by itself. So on this one I went 1 decimal place on the smaller volume, so I'm going to do that on this one. So the larger volume is approximately 3699.2 inches cubed. So the big thing when we're working with similar shapes is we're going to be using some proportions to help solve them. If you have any questions, please make sure you get a hold of me. Have a good day.